Yeah, hello guys. I'm Cyprian Ahura. Once again here to solve a particular question for you again. Well, here's the question. Calculate the standard Gibbs free energy for the reaction. This is the reaction equation. Given that its standard enthalpy and entropy changes are negative 91.8 kilojoule per mole and negative 198.0 joule per Kelvin, respectively. Now, this question might appear very simple, but if you're not too careful, you might fail. Now, here are the things you need to consider. Now, this is the formula for calculating the Gibbs free energy of a reaction. Delta G is equal to delta H minus T delta S. Now, this is the formula for calculating the standard Gibbs free energy for a particular reaction. Now, for standard values are denoted by either a bar or a knot or a degree sign. Anyhow, you might want to put it. Now, delta G naught is equal to delta H naught minus T delta S naught. This is the formula for calculating the standard Gibbs free energy of a particular reaction, where delta G naught stands for standard Gibbs free energy, delta H naught stands for the standard enthalpy of the reaction, and T for the standard temperature, and delta S naught stands for the standard entropy of a particular reaction. Now, look at this question, gave values here, two values here, and said respectively. Meanwhile, in the equation, you have enthalpy and entropy are called. So they're telling you, what this respectively is telling you is that these values are in accordance to how this has been listed. Negative 91.8 kilojoule per mole for enthalpy, while the last negative 198.0 joule per Kelvin for the entropy. So here I will going to say that delta H naught is equal to minus or negative 91.8 kilojoule per mole, and delta entropy, which is delta S naught, is equal to negative 198.0 joule per Kelvin. And the temperature, now this temperature might be tricky. Now, sometimes this reaction takes place at room temperature. However, this question did not tell you that this reaction is taking place at room temperature, but it is telling you that this reaction is taking place at standard values, which means that we know that our standard temperature is 0 degrees Celsius, which is equivalent to 273.15 Kelvin. Now, we're converting this 0 degrees Celsius, which is the standard temperature, to 273.15 Kelvin, since this reaction does not state categorically that this reaction is taking place at room temperature. So, now in this case, we've known the formula, which is just to input these values into the formula, and we're going to get our answers. However, not so fast. Look at something. Now, if we are to work with this, the values of the units here, they vary. We have our standard enthalpy in kilojoule per mole, whereas our entropy is in joule per Kelvin, and kilojoule and joule cannot move, except we must convert one to the other in order to tally. So that must be done. Always take that into cognizance. So here is the conversion factor in order to convert from joule to kilojoule. Now, 1 kilojoule per Kelvin is equivalent to 1000 joule per Kelvin. So we'll set out this conversion table, which is minus 198.0 joule per Kelvin. The conversion factor will write in such a way that the joule down can be able to cancel the joule up. So 1000 joule per Kelvin is giving you 1 kilojoule per Kelvin. So now, right about now, you can have joule per Kelvin can cancel joule per Kelvin. Now you now have negative 198.0 without a unit now, multiplying 1 kilojoule per Kelvin, dividing by 1000 without a unit. And if that happens, your entropy will now be equal to negative 198.0 times 1 kilojoule per Kelvin, which is what we obtain from there, divided by this 1000 here, which has no unit now. Working this out and divided by 1000, you have this answer right here as your delta S naught, which is your entropy, standard entropy, would equal to negative 0.198 kilojoule per Kelvin. Now, the units of of entropy now are now tallying with the units of our enthalpy. Our units of entropy, standard units of entropy, are now tallying with the units of enthalpy. So from here, we can now proceed with our calculations. Now, some of you might be confused about this table, how this table is arranged like this. This is a standard way for sciences making conversion factors, using conversion factors to make your conversions. However, if you're not conversant with this, there is a simpler method. Now, 1 kilojoule per Kelvin is equal to 1000 joule per Kelvin. So, delta S naught, which is standard entropy, is equal to minus 198.0 joule per Kelvin. Now, the unit, we don't know this, and that is what we're looking for. It's equivalent, the equivalent of this in kilojoule per Kelvin. So we'll do cross multiply now. If we cross multiply now, our entropy now multiplied by 1000 joule per Kelvin, and our 1 kilojoule per Kelvin multiplied by this negative 198.0 joule per Kelvin. And this will give us our entropy times 1000 joule per Kelvin. Sorry, we needed that. It's equal to 1 kilojoule per Kelvin. Omitted those per Kelvin there, multiply by negative 198.0 joule per Kelvin. Make this the subject of the formula. You have this, and voila, your answer is the same with what we've got in there. So for those of you who cannot use this particular table here, you can use this format as well. However, this is the standard way of doing it, especially for standard exams. Now, let's proceed with the question. So now we'll just bring in this formula here and input the values since we've known everything. Our delta G naught, which is the Gibbs standard Gibbs free energy, will be equal to negative 91.8 kilojoule per mole minus. Now you open your bracket, you put your value of T, that is the standard temperature of 273.15 Kelvin, times negative 0.198 kilojoule per Kelvin. This is the answer we got. That is the entropy. Now we'll work this out. Negative 91.8 kilojoule per mole minus bracket. We'll work what is inside the bracket. We got negative 54.1 kilojoule. Now remember from your maths, when there is a negative sign outside here, it changes the sign inside the bracket. So definitely this negative sign here will change this sign inside the bracket to become plus. So you're going to have negative 91.8 kilojoule per mole plus 54.1 kilojoule, and this, your delta G naught, is equal to now negative 37.7 kilojoule per mole. Notice that the units of temperature were in Kelvin, and it has done away with the per Kelvin that you had there, if you're wondering, in case. So this is your final answer. This is the standard Gibbs free energy for this particular reaction, for the production of ammonia gas. Thank you. If you have any question, you can put them down. If you have any observation, you can put them down. There's no problem. Once again, welcome.